In case this video goes blurry for a second or two, it's because I turned the manual focus off, so I don't think it's going to harm anything. But anyway, so here's a problem I'd like to do. I set up an equation, solve x to the fifth plus 2x to the fourth plus 3x cubed plus 4x squared plus 5x plus 6 equals 0. And I mentioned that when it comes to polynomials, if you have a fifth degree equation, there is no general technique for solving it. It literally is impossible to find an algebraic technique that will solve this, kind of like the quadratic equation method. There's no exact method for getting an exact answer. So our best chance is to estimate an answer. And so here comes Newton's method. Now, I happen to know, if you look at this, x can't be positive, because if you plug a positive number, all that's positive can never equal 0. So I know the answer, if there is one. Well, actually there's at least one answer, because fifth degree polynomials are going to cross the x-axis at least once. So I happen to have done this problem before, and I'm just going to guesstimate x equals -1 as my starting point. So, but the answer is around -1.49, I think. So we'll figure that out. All right. So I want this to be my function, f of x. It's already set equal to 0. It has to be equal to 0. So f of x is this polynomial, and the derivative would be 5x to the fourth plus 8x cubed plus 9x squared plus 8x plus 5. And did I do that right? Looks like it. Okay. By the way, I went on Wikipedia, looked up Newton's method. It's actually sometimes known as the Newton-Raphson method. R-A-P-H-S-O-N. Raphson apparently improved on Newton. Newton only came up with this method for polynomials. Raphson, who's kind of an obscure mathematician from around 1700, he made it generalized and more like our modern form than I'm showing you. So, but anyway, it's if you have an interest, go on Wikipedia. You're going to find all kinds of deep discussion about Newton's method. It's a very rich subject, and too much to go into in a calculus class. But there are some really nice things there. Okie dokie. All right, so I have to remember my new x value. X new is going to be the initial x, or some input value x, you might call it x old, minus the function, parentheses, x to the fifth plus 2x to the fourth plus 3x cubed plus 4x squared plus 5x plus 6, divided by its derivative, 5x to the fourth plus 8x cubed plus 9x squared plus 8x plus 5. And on a calculator, I'm going to need to put that in parentheses, so I'm just going to go ahead and put that in parentheses. All right, so that's what we're up against. And let's see. I'll set up my table here. So I have the n, or the iteration number, and x n. And so my starting guess, as I said, I'm going to use -1. All right, so I'm going to plug -1 into all that and see what I get. All right, so I want to show you what that looks like. And so let me see. The trick is to hold this up so you don't get a lot of glare. And so I'll have to fiddle with this. I notice it's not, there we go, now it's in focus. Okay, so I'm going to punch in -1. So on my calculator, okay, -1, and there's a store button, STO, right there. Store, and this is my X button. It says X variable. Some calculators call it something a little bit different. They might have X, T, and theta or something. Store in the X. So -1, store X. I'll hit enter, the equal sign, enter, and so my calculator believes that X equals -1. All right, now I need to punch in that Newton's method formula there. So let me just punch it in. Okay, it's going to be, it'll take me too long to make sure you're reading all this. X minus parentheses x to the 5th plus 2x to the 4th. I'll just go ahead and punch it in. Plus 2x to the 4th plus 3x cubed plus 4x squared plus 5x plus 6. Alright, so x, here you can see if I did that right. And now I have to divide. So now I had put all that in parentheses, so I hit divide, then left parentheses, and I'll punch in the denominator. Alright, so 5x raised to the 4th plus 8x cubed. Sorry, this takes a little bit, that time, doesn't it? Plus 9x squared plus 8x plus 5. Alright, close parentheses. Alright, got that? So I'm going to double check it myself, make sure I've got all that correct. So bear with me here. Ax to the 5th plus 2, 3, 4, 5, 6. Yeah, I think it's correct. Okay, now I am not done yet. I'm going to hit store x. Okay, so I got this calculation in my calculator, and now I'm going to hit store x. So whatever I get is going to become the new x. And now I hit enter, and voila, I get minus 2. Okay, so that whole calculation with x equals -1 gives me -2. So let me write that over here. And so for the first iteration, I get -2. All right, now here we go. A lot of these graphing calculators usually have a buffer where you can bring up a past calculation or several calculations. And I'm going to hit, see above enter? Oops, okay, there it says entry. So I hit the second button and my enter button. It brought up that calculation. And it's going to store it in x. In other words, my new x is -2, and then it calculates it and gives me the next x, which is going to be probably a decimal number. Yeah, a decimal number. So I'm going to write that on the board. And I'll then show you that one more time. So the next go around, I got minus 1.707, 317, 07317. Alright. There we go. And it probably, if I had to guess, it probably repeats these 5 digits. Yeah, it's an irrational number. I'm sorry, it's a rational number, it's a fraction. So it's going to repeat. Anyway, same idea again. I hit second, enter. There's the calculation. So it stored the last answer. It had stored the last answer. I calculate again, hit equal, and then it comes up with a new number. All right. So I'm just going to repeat that process and see what happens. Now this is converging somewhat more slowly. -1.54333037221. So if I do that again, same process, hit second enter. On the 4th time, I've got, let's see, -1.49532631616. Do it again. And this is going to take a couple more steps, I think. -1.4918, 154, 585. Fewer decimals that time. I'll do it again. And it's starting to converge, so I'm going to extend my table. I know this is a long one, and if I wanted to do a long one, and later I do my Davidson-Carver method video, this will get to the answer quicker. So a friend of mine who used to teach with me, he and I both came up with a improvement on Newton's method during a church sermon of all places. Anyway, it's a long story. I'll tell you that in the other video. All right, so where am I at here? This when n equals 6, my 6th term is -1.491797988857. Now we're getting close to something. Yeah, we're getting pretty close to an answer here. Let me do it again. and number 7 here, minus 1.49179, 7988. So you should be trying this on your calculator, and if you don't, if your calculator doesn't print out as many decimal places, it'll round off to what I'm getting. So look at that, I'm already good out to maybe 9 decimal places, and if I want a little bit better, now usually, if you're like applying this in engineering or something, 4 or 5 decimal places is usually plenty of accuracy, but I'll just keep going. Negative 1.49 179 7988 14. Huh, look at that. It repeated again. So, because these are the same, you may as well stop, because you're just going to keep getting this number. So we've got the root of this equation calculated, accurate out to I don't know, 11 places maybe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Accurate out to 11 decimal places. And so there you go. It took 7 steps. It took 7 steps. When I do this later with the Davidson-Cartwright method, I can get here in, I think, 4 steps. But it's a lot more complicated. No one really uses my method or our method, but I like to show it as an extra goodie for this class. Okay, well, some comments here. This I'll do one more with involving a trig function just for the fun of it. I think it'll go fast. And so another thing I'd like to say is that it's a curiosity. You can make a mistake and still get the correct answer. For example, if you had a 7 here instead of an 8, I think I'll still get this answer. Now it may take another step or two. If you left off a term, it might take a couple more steps. So it's something interesting about the Newton's method, in that you can make a mistake, or if you write this down and manually entering it, which is a hard way of doing it, if you enter the wrong number, you'll still get the right answer, but it may take longer. And so it's a forgiving method, believe it or not. So it's kind of interesting that you can make a mistake and still get the right answer. Now, I'm not so sure. I don't think you're going to get the right answer if you make a mistake with the original function. But if your derivative is a little bit off, then it could take you more steps to get to the correct answer. So, I always found that pretty interesting. And I'll at the end of this video, I'll mention another couple of things that are you kind of need to know about Newton's method. Okay, there are other ways to solve this, by the way. There's one called the bisection method. And in the bisection method, you guess 2 numbers, say an x1 and an x2, and if one's negative, one's positive, then you take their average, and that becomes your next guess. And then if that's positive, you would average it with a negative, and you just keep averaging, and you get closer and closer. Now it's a lot slower than Newton's method, the bisection method. It should work about every time, and Newton's method does not always work. Most of the time it does, but there are exceptions. That's what I want to show you later. But a bisection method has what's called, I believe, linear convergence, and this has quadratic convergence. So I'll try to explain that later on. Okay, a lot of stuff to talk about. So I'm going to erase this, do one more of these, and we'll go from there.